Stack sortable permutations. The initial setup of our topic for this section sounds similar to the well-known game of Hanoi Towers. Assume we have a permutation P equals to P1, P2, P3 until Pn, and we want to sort its entries to get the identity permutation 1, 2, 3 until n. Our only tool is a stack, a vertical array that can hold entries in increasing order, that is, the smallest one on top and the largest one at the bottom. The numbers enter the stack in the order in which they occur in the input permutation P. We take P1 and put it in the stack. Now take P2. If P2 is less than P1, then it is allowed for P2 to go in the stack on top of P1. So we will put it there. If P2 is greater than P1, however, then first we take P1 out of the stack and put it to the first position of the output permutation and put P2 into the stack. We continue this way. At step I, we compare Pi with the element r equals to P alpha I minus 1 currently on top of the stack. If Pi is less than r, then Pi goes on the top of the stack. If not, then r goes to the leftmost empty position of the output permutation, and Pi gets compared to the new element that is currently on the top of the stack. The algorithm ends when all n entries passed through the stack and are in the output permutation. Pi of p. See figure 14.3 for an example of this procedure. Example 14.19. Let p equals to 2, 4, 1, 3. Then the stages of our sorting procedure are shown in figure 14.3. If the image S of p under this stack sorting operation is the identity permutation, then we say that P is stack sortable. So the previous example shows that 2413 is not stack sortable. Which permutations are stack sortable? To answer this natural question, we first analyze the effect of the stack sorting operation S to pairs of entries in P. Proposition 14.20. Let P be a permutation, and let A less than B be two entries of P. Then 1. If A precedes B in P, then A precedes B in S of P. 2. If B precedes A in P, then there is no element C located between A and B in P, so that C is greater than B is greater than A, then A precedes B in S of P. 3. If B precedes A in P and there is an element C located between A and B in P so that C is greater than B greater than A, then B precedes A in S of P. Note that this happens when the entries A, B, and C form a 2, 3, 1 pattern. Proof. 1. As A precedes B in P, A will enter the stack before B. As A is less than B, this means that B cannot even enter, let alone leave the stack before A does. So, A precedes B in S of P. 2. In this case, the stream of P between B and A is a decreasing subsequence S. The elements of S enter the stack starting with B, then they pile up on top of each other, with A entering the stack last and getting, therefore, to the top of the stack. So A will be the first element of S to leave the stack. In particular, A leaves the stack before B, and thus A precedes B in S of P. 3. In this case, B has to leave the stack before C enters it. On the other hand, C has to enter the stack before A does. Therefore, B leaves the stack before A could even enter it. So B precedes A in S of P. Theorem 14.21. A permutation P is stack sortable if and only if it avoids the pattern 231. Proof. If there is a 231 pattern in P formed by the entries A less than B less than C, then part 3 of the previous proposition shows that B will precede A in S of P. So S of P cannot be the identity permutation. If there is no 231 pattern in P, then any pair A less than B of entries falls either into part 1 or into part 2 of the previous proposition and will therefore be sorted. so most permutations are not stack sortable. To increase the number of permutations that can be sorted using our stack, we can take S of p and pass it through the stack again, following the same rules. If the obtained permutation S of p is the identity permutation, then we say that p is a two-stack sortable. Two-stack sortable permutations are more difficult to characterize, let alone enumerate, than stack sortable permutations. One reason for this difficulty is that the two-stack sortable property is not monotonic. That is, there are instances when P is two-stack sortable, but a subsequence P prime is not. Example 14.22. Let P equals to 35241, then S of P equals to 32145, and S of P equals to 12345, so P is two-stack sortable. Now let P prime equals to 3241, then S of P prime equals to 2314, and S of P prime equals to 2134, so P prime is not two-stack sortable. For this reason, we cannot hope for a characterization of two-stack sortable permutations by pattern avoidance only. However, we can still use a similar concept if we stretch the definition of pattern avoidance a little bit. Theorem 14.23. A permutation P is two-stack sortable if and only if it does not contain a 2341 pattern, and it does not contain a 3241 pattern, except as a part of a 35241 pattern. Proof. First, we prove that the only if part. Assume entries A is less than B, less than C, less than D of P form a 2341 pattern. Then it follows from proposition 14.20 that entries A, B, and C form a 231 pattern in S of P, implying that S of P is not stack sortable. Now assume that entries W less than X less than Y less than Z form a 3241 pattern in P that is not part of a 35241 pattern. Proposition 14.20 then implies that both X and Y precede W in S of P. If there are no entries between X and Y in P that are larger than both of them, then proposition 14.20 also implies that X precedes Y in S of P, and we are done as W, X, and Y form a 231 pattern in S of P. If there is an entry T between X and Y that is larger than both of them, then keeping in mind that the 3241 pattern Y, X, Z, U is not part of any 35241 pattern, the pattern Y, T, X, Z, U must be a 34251 pattern. However, that implies that entries Y, T, Z, and U form a 2341 pattern, and we have seen in the previous paragraph that such a pattern prevents P from being two-stack sortable. Now we prove the if part. It suffices to show that if S of P is not stack sortable, then P had to contain one of the two forbidden configurations mentioned in the theorem. If S of P is not stack sortable, then it contains a 231 pattern. Let E less than F less than G be the entries of one such pattern. Then by proposition 14.20, E was the rightmost of these three entries in P, and there had to be an entry H in P that separated both F and G from the entry E. If F preceded G in P, then FGHE was a 2341 pattern in P, and we are done. If not, then G preceded F in P. We know that F precedes G in S of P, which implies that there was no entry between G and F in P that was larger than both of them. So GFHE formed a 3241 pattern in P that was not part of a 35241 pattern, completing the proof. The number of two-stack sortable n permutations is known to be 2 divided by n plus 1 times 2n plus 1 times 3n choose n. This formula has at least 4 different proofs, all of which are somewhat complicated. We can certainly generalize our definitions. We say that a permutation P is T-stack sortable if S to the T of P is the identity permutation. In other words, passing P through the stack T times, we get the identity permutation. Note that all T-stack sortable permutations will necessarily be U-stack sortable permutations for all U which is greater than T. While we are not able to enumerate T-stack sortable permutations, we will prove several interesting statements concerning them. To that end, we need to have a deeper understanding of the effects of the stack sorting operation. Lemma 14.24. Let P equals to L and R be an n permutation, where L denotes the string on the left of the entry n, and R denotes the string on the right of the entry n. Then we have S of P equals to S of L, followed by S, followed by R, followed by N, S of L, followed by S of R, followed by N. Proof: as P passes through the stack, first the entry that belong to L enter the stack. They all leave the stack before N entries, creating S of L at the front of the output permutation. Then N enters the stack. Then all the entries belonging to R pass through the stack, creating S of R in the output permutation, while N stays in the bottom of the stack. Finally, N leaves the stack. We mentioned that the property S of P equals to S of L followed by S of R followed by N in fact defines the stack sorting operation. That is, the stack sorting operation is the only operation defined on all finite permutations that has this property. Corollary 14.25. All n permutations are n-1 stack sortable. Proof: we prove this statement by induction on n. For n equals to 1, the statement is trivial. Now suppose the statement is true for n-1 and prove it for n. Let P equals to L and R be any n permutation. Lemma 14.24 means in particular that S of P always ends with its largest entry, and also if R is empty, then S of Ln is equals to S of L followed by n. Iterating this, S to the n-1 of P is equals to S to the n-2 of S of L followed by S of R followed by n, which is equals to S to the n-2 of S of L followed by S of R, then followed by n. This later is the identity permutation, as S of L followed by S of R is a permutation of length n-1 and therefore is n-2 stack sortable by the induction hypothesis. Corollary 14.26. For all n permutations P, the T-sorted image S to the T of P ends in the string n minus T plus 1, followed by n minus T plus 2, and so on, followed by n. Proof: immediate by induction on T. The property that S of P is equals to S of L followed by S of R followed by n enables us to translate the stack sorting operation into the language of binary plain trees. If P is an n permutation, we associate a rooted tree T of P to P as follows. The root of T of P is a vertex labeled n, the largest entry of P. If A is the largest entry of P on the left of n, and B is the largest entry of P on the right of n, then the root will have two children. The left one will be labeled A, and the right one labeled B. If n was the first, respectively last entry of P, then the root will have only one child, and that will be a left, respectively right child, and it will necessarily be labeled n-1, as n-1 must be the largest of all remaining elements. Define the rest of T of P recursively by taking T of P prime and T of P prime prime, where P prime and P prime prime are the substreams of P on the two sides of n, and affix them to A and B. Example 14.27. If P equals to 2, 6, 3, 4, 9, 8, 1, 7, 5, then T of P is the tree shown in figure 14.4. The tree T of P is called the decreasing binary tree of P. It is indeed a binary tree, that is, each vertex has 0, 1, or 2 children. Given T of P, we can easily recover P by reading T according to the tree traversal method called in order. In other words, first we read the left subtree of T of P, then the root, and then the right subtree of T of P. We read the subtrees according to this very same rule. Now let us read the tree T of P in post order instead. In other words, let us first read the left subtree of T of P, then the right subtree of T of P, and finally the root. Example 14.28. The tree shown in figure 14.4 is the decreasing binary tree of P equals to 2, 6, 3, 4, 9, 8, 1, 7, 5. Read in a post order, it yields the permutation 2, 3, 4, 6, 1, 5, 7, 8, 9. The alert reader might have noted that reading T of P in post order, we precisely get the permutation S of P, the image of P under the stack sorting operation. This is no accident. Proposition 14.29. Let P be any n permutation. If we read the decreasing binary tree T of P in post order, we obtain S of P. Proof. We prove the statement by induction on n, the initial case of n equals to 1 being trivial. Assume the statement is true for all positive integers less than n. Let P equals to L and R, and let us read T of P in post order. We start with the left subtree, which is in fact T of L. Reading that in post order, we get S of L by the induction hypothesis. Then we have to read the right subtree, which is T of R. Reading that in post order, we get S of R by the induction hypothesis. Both L and R are shorter than P. Finally, we read the root, which is n, so we obtained the permutation S of L followed by S of R followed by n, and we are done by proposition 14.24. Recall that we say that I is a descent of the permutation P equals to P1, P2, P3 until Pn if Pi is greater than Pi plus 1. Similarly, we say that I is an ascent of the permutation P if Pi is less than Pi plus 1. Let d of P denote the number of descents of P. Note that if P is an n permutation, then n minus 1 minus d of P is equal to the number of ascents of P. Indeed, if I is a descent of P, then I is an ascent of the complement of P. It follows immediately that there are as many n permutations with k descents as there are with n minus 1 minus k descents. If we consider decreasing binary trees again, it is straightforward to verify that P has k descents if and only if T of P has k edges connecting a vertex to the right child of that vertex. Let us now enumerate T-stack sortable n permutations according to their descents. Let Wt of nk be the number of T-stack sortable n permutations with k descents. The following table shows the numbers Wt of nk for small values of the parameters. These data seem to suggest that Wt of nk is equals to Wt of n minus 1 minus k for all positive integers n kt. If true, this would be a surprising theorem, as there seems to be nothing symmetric about T-stack sortable permutations, these obscure creatures. The complement or reverse of a T-stack sortable permutation does not need to be T-stack sortable. Try 213 or 132 with the T equals to 1. So these easy bijections will not work. In the rest of this chapter, we prove this nice symmetry. We will also see the tree interpretation of the stack sorting operation at work. The following simple map will be our main tool. Definition 14.30. Let F be the map defined on all finite permutations as follows. F of 1 is equals to 1. If P is an n permutation and P equals to L and R, and neither L nor R is empty, then f of P is equals to f of L followed by n followed by f of R. If P is an n permutation and P equals to Ln, then f of P is equals to n followed by f of L. And if P is an n permutation and if P is equals to nr, then f of P is equals to f of R followed by n. In words, if the maximal entry n is at neither endpoint of B, then we keep n fixed and apply f recursively on both sides of n. If n is at either endpoint, then we put n into the opposite endpoint and apply f recursively. When we apply f recursively to L and R, then we treat L and R as permutations. This means that the maximal element of L will take over the role of n when f of L is formed, and the maximal element of R takes over the role of n when f of R is formed. Example 14.31. If P equals to 1 to 3, then f of P equals to 3 to 1. So if P equals to 4, 1, 2, 3, then f of P is equals to 3, 2, 1, 4. Example 14.32. If P equals to 1, 4, 2, 3, then f of P equals to 1, 4, 3, 2. Example 14.33. As a consequence of the preceding examples, if P is equals to 4, 1, 2, 3, 9, 5, 8, 6, 7, then f of P equals to 3, 2, 1, 4, 9, 5, 8, 7, 6. The following proposition shows that the effect of f on the number of additions of a permutation is precisely what we will need. Proposition 14.34. For any n permutation P, the equality d of P plus d of f of P is equals to n minus 1 holds. Proof. We prove this claim by induction on n, the initial case being trivial. First, assume that n is at neither endpoint of P, so P is equals to L and R, and f of P is equals to f of L followed by n followed by L f of R. Say that n is in the ith position of P, then we have d of P is equals to d of L plus d of R plus 1, and d of f of P is equals to d of f of L plus d of f of R plus 1. So d of P plus d of f of P is equals to d of L plus d of R plus 1 plus d of f of L plus d of f of R plus 1, which is equals to I minus 2 plus n minus I minus 1 plus 2, which is equals to n minus 1, which was to be proved. We used the fact that d of L plus d of f of L is equals to I minus 2, and d of R plus d of f of R is equals to n minus I minus 1 by the induction hypothesis. Now assume n is in the last position and P equals to Ln. Then clearly d of P is equals to d of L, while d of f of P is equals to d of n followed by f of L. Then take the d, which is equals to d of f of L plus 1. And the proof follows by induction. Similarly, if n is in the first position and P is equals to nr, then d of P is equals to d of nr, which is equals to 1 plus d of r, while d of f of P is equals to d of f of r followed by n, which is d of f of r, and again, the proof follows by induction. Our f maps permutations with k descents into permutations with n minus 1 minus k descents, so that we could use f to prove that the sequence Wt of nk, where 0 is less than equals to k, is less than equals to n minus 1, and is symmetric. The sequence Wt is symmetric. We must show that f preserves the T-stack sortable property. The following lemma is the key element of the proof of this. Lemma 14.35. For any permutation P, the equality S of P equals to S of F of P holds. Proof. We prove the statement by induction on n, the length of P. The statement is trivially true if n is equals to 1. Now let us suppose it is true for all positive integers less than n. 1. Suppose first that the entry n is at neither end of P, and let P equals to L and R. Then S of P is equals to S of L, followed by S of R, followed by n, which is equals to S of F of L, followed by S of F of R, followed by n, which is equals to S of F of L, followed by n, followed by F of R, which is equals to S of F of P. 2. Now suppose that the entry n is in the first position, so P is equals to n followed by R. Then S of P is equals to S of R followed by n, which is equals to S of F of R followed by n, which is equals to S of n followed by F of R, which is equals to S of F of P. 3. Finally, if the entry n is in the last position, so P is equals to Ln, then S of P is equals to S of L followed by n, which is equals to S of F of L followed by n, which is equals to S of n followed by F of L, which is equals to S followed by F of P. So the statement is true in all cases. Again, we used the fact that S of L is equals to S of F of L, and S of R is equals to S of F of R by the induction hypothesis. Corollary 14.36. The permutation P is T-stack sortable if and only if F of P is T-stack sortable. Proof. Both statements are true if and only if the permutation S of P is equals to S of F of P is T-1 stack sortable. Now the proof of our duality theorem is immediate. Theorem 14.37. For all positive integers n, k, t, the equality Wt of nk is equal to Wt of n minus 1 minus k holds. Proof. Corollary 14.36 and proposition 14.34 show that F bijectively maps the set of T-stack sortable n permutations with k descents onto that of T-stack sortable n permutations with n minus 1 minus k descents. In order to get a deeper understanding of this proof, let us try to go through it in terms of decreasing binary trees. A right or left edge is an edge between a vertex and its right child or left child. What we want to prove is that there are as many decreasing binary trees on n vertices corresponding to T-stack sortable permutations with k right edges as there are with k left edges. Our map F takes a tree T of P and goes through its vertices starting at the root. If the root has two children, then the two edges adjacent to the root are unchanged. However, if the root has only a left edge, then the entire left subtree of the root will be moved to the right of the root and become its right subtree. Similarly, if the root has only a right edge, then the entire right subtree of the root will be moved to the left of the root and become its left subtree. Then we proceed to the vertices immediately below the root and apply the same rule. We continue this way until all vertices have been treated. This procedure clearly turns vertices with only a left child into vertices with only a right child. If a vertex had two children in T of P, it will have the same two children in T of F of P. This proves, again, that D of P plus D of F of P equals to n minus 1 as the number of left edges of T of P is equal to the number of right edges of T of F of P. To see that S of P is equals to S of F of P, we need to show that the tree T of P and the T of F of P yield the same permutation when read in post order. To see this, note that if a vertex X has only one child Y, then as far as the result of the post order reading is concerned, it does not matter whether Y is a left child or a right child of the X. In both cases, the post order reading will first go through the subtree rooted at Y, then go to X. On the other hand, the only effect of the map F on P is precisely this. That is, F turns each single left child into a single right child and vice versa. So F has no effect on S of P as we have claimed. Note that we have proved a little more than we planned. We proved that each entry X of P has the property that the subtree of T of P rooted at X and the subtree of T of F of P rooted at X yield the same result when read in post order. Originally, we only wanted to prove this for the full trees, that is, the subtrees of the entry n. Example 14.38. The decreasing binary trees of P equals to 3, 5, 6, 1, 2, 4, and the F of P equals to 5, 3, 6, 4, 2, 1 yield the same permutation, 3, 5, 1, 2, 4, 6, when read in post order. The same is true for the subtrees of any given entry. Notes: as pattern avoidance is the youngest of all areas covered in this book, it is also the one whose progress is the fastest. For this reason, this is the chapter that changed the most since the publication of the first edition. For a more thorough treatment of the topics discussed in this chapter, the reader is advised to consult the combinatorics of permutations by the present author, which devotes chapters 4, 5, and 8 to the subject. Chapter 4 contains the proof of the Stanley-Wilf conjecture by Marcus and Tardish. We have included several exercises that ask for the numbers Sn of Q1, Q2 of n permutations avoiding both patterns Q1 and Q2. Further results on this subject are available in references. The solution of the Stanley-Wilf conjecture implies that the limit L of Q equals to the limit of the nth root of Sn of Q when n goes to infinity exists. This limit provides a good way of measuring the growth rate of the sequence Sn of Q. It was previously conjectured that if Q is in Sk, then L of Q is less than or equals to k minus 1 to the square. However, this conjecture has recently been disproved. A counterexample is given by the inequality L of 1324, which is greater than 9.35. As far as a lower bound is concerned, it is known that L of Q is greater than or equals to k squared divided by e to the cube for all Q in Sk.